In this video, I'm going to show you how to compute limits of reciprocal functions. First of all, we want to compute the limit as x approaches positive infinity of 1 over x. And the way we're going to do this is we're going to think about this function graphically. What does 1 over x look like on a graph? Well, why don't we think about plugging in some points. When we plug in x equals 1, the output is 1, so that corresponds to the point 1, 1 on the graph. When we plug in x equals 2, the output is a half, so 2, a half. Then it goes 3, a third, and so on. So we see that the graph is following a path downward with an asymptote at the x-axis. Now the limit as x approaches infinity is just asking what's happening to the value of the function as the x value gets larger and larger, and we see that the function value is dropping down to 0. You can think about plugging in even larger values of x. If x equals 1,000, then we've got 1 over 1,000 for the function value, which is really close to 0. Even closer if we plug in x as 1,000,000. So we see that the limit as x approaches infinity of 1 over x is 0. Okay, so how about as x approaches negative infinity? Well, why don't we continue this graph over to the left? Now, we can't plug in 0 because that would make the denominator 0. So 0 is a vertical asymptote of this graph. And we see that when we're approaching from the right, if we bring our x down from 1 to a half, then 1 divided by a half is 2, so it's going up. It approaches infinity as it reaches that vertical asymptote of 0. Okay, but we want to consider x approaching negative infinity, all the way this way, so we have to get beyond this asymptote. What happens at this asymptote doesn't really matter. So let's keep on plugging even more negative values in for x. How about x equals negative a half? Well, 1 divided by negative a half is negative 2, so we have this point here, negative a half, negative 2. Then when x equals negative 1, 1 divided by negative 1 is just negative 1. When x equals 2, 1 divided by negative 2 is negative a half. Then 1 divided by negative 3 is negative a third. So we see that the graph looks very similar on the other side, except it's flipped into the negative side of the y-axis. So what's happening as x approaches negative infinity? So the function outputs are still approaching 0. So that's the limit, 0. Okay, so how about the limit as x approaches positive infinity of 1 over x squared? Well, what does the graph of 1 over x squared look like? When x is 1, the output is still 1 over 1 squared, which is 1, so we still have this point here. When x is 2, the output is 1 over 2 squared, which is 1 over 4, so it's dropping down a lot quicker to approach the x-axis. And that means still, as x approaches infinity, the function value is getting closer and closer to 0. So that's the limit. Limit is 0. Okay, and then the limit as x approaches negative infinity? Let's continue the graph over to the left. What does the rest of this graph look like? Well, we still have a vertical asymptote at x equals 0 because we can't plug in 0 into that denominator. And as the function approaches x equals 0 from the right, the denominator gets smaller and smaller and the function is shooting up to positive infinity. From the left, it's pretty similar. But unlike last time where the function branch was flipped over into the negative region of the y-axis, this time the function values are still positive because a number x squared, even if we plug in a negative for an x, a negative squared is a positive. For example, at the point negative 1, 1 over negative 1 squared is just 1 over 1, which is 1. So this graph is just going to be symmetric about the y-axis here. So it'll go up like this towards positive infinity as x approaches 0, and as x approaches negative infinity, it's going down, down, down to 0. So we see that the limit as x approaches negative infinity, while the function is just dropping down to 0, so the limit is 0. Alright, so there's a pretty clear pattern here. All of our answers are 0. So why don't we go ahead and write the general statement of this pattern? The general statement is that for any positive integer n, we have both that the limit as x approaches positive infinity of 1 over x to the n is equal to 0, and that the limit as x approaches negative infinity of 1 over x to the n is also equal to 0. So this is the important takeaway here. Whenever you have 1 over x raised to some positive power, then the limit at positive or at negative infinity, both are going to be 0. Alright, so previously we talked about limits at positive and negative infinity, and now we're going to talk about limits at 0. So let's first consider for the function 1 over x, what is the limit as x approaches 0 from the positive side? Well, Coming from the positive side, as x approaches 0, the function is shooting up and up and up. And that just happens because x is becoming a smaller and smaller positive number. So when we have 1 over a very small positive number, 1 divided by a very small positive number is a very big positive number. Like 1 divided by 100th is how many hundredths are in 1? Well, 100. 1 divided by a millionth is how many millionths are in 1? Well, a million. So the result keeps getting larger and larger. And we see that the function value is shooting up to positive infinity. So that's the limit from the right as x approaches 0. It's positive infinity. Okay, and then how about on the left? Well, as x approaches 0 from the left, we're in a pretty similar situation. The input x is getting closer and closer to 0, but this time it's negative. So the magnitude of the result is still getting larger and larger, but the sign of the result is always negative. For example, 1 divided by negative a millionth is negative a million. And we see that the function is shooting down, down, down to negative infinity. So that's the value of this limit. As x approaches 0 from the left, it's negative infinity. Okay, and now how about the limit as x approaches 0? Just the overall limit? Well, we see that the right limit and the left limit don't match up. The right limit goes to positive infinity, whereas the left limit is at negative infinity. So the overall limit as x approaches 0 does not exist. Alright, and how about the same questions for the function 1 over x squared? First of all, what is the limit as x approaches 0 from the positive side? Well, looking at our graph, it's shooting up, 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 just like before. And that's happening for the same reason. When we input a very, very small number for x squared is also a very small number, and 1 divided by a very small number is a very large number. So as x approaches 0 from the positive side, we see that this function is going to positive infinity. Now, how about as x approaches 0 from the negative side? Well, again, it's a pretty similar argument. X is getting closer and closer to 0, so x squared is getting closer and closer to 0, and 1 divided by a very small number is a very large number. But unlike last time, where the sign was negative, the sign this time is positive. And that happens because even when we choose a negative input value for x, since there's a squared on the x, squaring gets rid of that negative sign. So the overall result is positive, and we see the function approaches positive infinity again as x approaches 0 from the left. So this limit is also positive infinity. And now we see that the right limit and the left limit match up. They're both positive infinity, and that means the overall limit as x approaches 0 of 1 over x squared is positive infinity. Alright, so let's go ahead and write down the general rule. The general rule is that for any positive integer n, we have two cases. First of all, if n is odd, then the limit as x approaches 0, 1 over x to the n, does not exist. Whereas if n is even, then the limit as x approaches 0, 1 over x to the n, is equal to positive infinity. And you can see this in our examples. When the power on x was just 1, the overall limit did not exist. Whereas when the power on x was 2, an even number, the overall limit came out to infinity. And that kind of pattern extends to any positive integer n. So now that we know the pattern behind limits of reciprocal functions, let's go ahead and apply it to an example. So here's our example. We want to compute the limit as x approaches 2 of negative 3 divided by x minus 2 to the 4th power. Now you'll see that if we try direct substitution, substituting 2 for x, we get a 0 in the denominator. So that's no good. So we need to try to simplify our limit somehow. And one way that we can simplify this limit is through a substitution. Let's just define u equals x minus 2. That way we'll lump this whole x minus 2 expression into a single variable in the denominator. Now we know that as x approaches 2, we have that u approaches x minus 2, which is 2 minus 2, which is equal to 0. So we can phrase the limit in terms of u as follows. This becomes the limit as u approaches 0 of negative 3 over u to the 4th power. So there's the result of our substitution, u equals x minus 2. Now this limit is beginning to look familiar. We are familiar with limits of the form 1 over our variable raised to some power. So why don't we rephrase this limit like that? So we'll just bring out that negative 3 in front of the limit. So we'll have negative 3 times the limit as u approaches 0 of 1 over u to the 4th. And hey, we know this limit. 1 over our variable to the 4th as our variable approaches 0. Since 4 is an even number, this limit is always going to come out to positive infinity. So this limit is coming out to positive infinity, but we also have that negative 3 multiplying it. So negative 3 times positive infinity. 3 times infinity is still just infinity, but our negative sign turns this into a negative infinity. So there we go. There is the value of our limit. It approaches negative infinity. So now we know how to compute limits of reciprocal functions. And in the future, we'll continue to gain a lot more practice computing limits, including limits of exponential, logarithmic, radical, trigonometric functions, and so on.